Assalamualaikum and good day for everyone. So now I will continue my lecture for chapter 6 which cover today is subtopic 6.5. So in this chapter there are 8 subtopic. So for today I will cover in this video is for subtopic 6.5 which is capacitor bank protection. Okay, first we go to this MV capacitor unit and capacitor element. So we can see here this is the capacitor unit, okay, which include capacitor element inside the capacitor unit. So for this element, there are several capacitor that installed in that capacitor unit. Okay, here is the switch step bank, which is a combination of several so-called switch step banks, which is each bank being separately controlled. So as we can see here, there are 4 banks here, which include 4 capacitor, and this capacitor is switched separately based on the requirement from the system. Okay, this is energization process of the capacitor bank will cause current and voltage transients during the process. Means that when we energize or when we switch the capacitor bank, the problem is there are currents and voltage transient happen during that process. Okay, and then the upstream network is considered to be a pure inductance L up, such that by using this formula, okay, upstream network is a network before capacitor bank is connected. So that is the meaning of the upstream network. Okay, by using this formula, we can calculate what is the pure inductance or L up. Okay, by using this formula, where we can see here, SC is the short circuit power at the capacitor connection point, and Vn is the nominal phase-to-phase voltage. Okay, and then ISC is the symmetrical three-phase short circuit current at the capacitor connection point. So this formula, L up times with the omega here. So then from this formula, we can calculate what is the L up, which is pure inductance of the system. Okay, next you can see here is a circuit for capacitor bank, which includes C here, which is equivalent to single phase diagram of a fixed bank. And then here is the L. You can see here L is represent as the switching device. Okay, the connection linking the switching device such as contactor, circuit breaker, switch or cable to the capacitor bank is considered to be a pure inductance. So L, which is 0.5 microhenry per meter, which correspond to an impedance of 0.1571 ohm per kilometer for 50 Hz system. Okay, this is the value for this L for 50 Hz system to make sure that the transient of the system is reduced when capacitor bank is switched. Okay, and then this is the L up, which represent as the L inductance for upstream network inductance, and L represent as the inductance of the connection linking the switching device to the capacitor bank. Okay, here is the expression of the peak inrush current, okay, which is renamed as I rush, okay, peak inrush current. Okay, this happened during the capacitor bank switch. There are I rush happen, and the value is very high during for certain second, and this is the formula, okay, which include Vn. Vn is the nominal phase-to-phase voltage, and C represent as the capacitor, and L up is the inductance for upstream, and L represent only a few meters of cable and is then negligible in relation to L up. So L value is neglect. So from this formula, and then we get the I rush by uh, by neglect the L value, so we get this formula for I rush. Okay, then this is the formula for the natural frequency of this current, which is F naught is equivalent to I over 2 pi square root L up C. Okay, then we have to compare the peak current with the nominal current of the bank. So this is the nominal current of the capacitor bank, okay, N cap is equal to C omega. Omega is equivalent to 2 pi F times Vn and divided by square root 3. Okay, this is the formula for nominal current of the capacitor bank. So we have to compare. So we have to compare or make it in ratio I rush divided by I and capacitor, which is equal to this formula. Okay, and then this is the formula for L up. Omega is equivalent to V square divided by S, and this is the formula for Q equal to C omega V squared. So from this formula, we can get what is the L up, okay, by divide this formula with the omega, and then from this formula, we can rearrange the formula and get the formula for C, which is equivalent to Q divided by omega V square. So the formula for L up and the C, we have to substitute in this formula, okay, L up and capacitor. So then when we substitute the formula and rearrange the formula, we can get the ratio of the I rush divided by I and cap is equal to this formula. Okay, and then we get the F naught is equal to this formula, where F is the network frequency, which is 50 or 60 Hertz. So for Malaysia, our frequency is 50 Hertz. Okay, next we go to example for a capacitor band protection. Okay. If we take the example of a fixed, 250 kVAR bank with a phase-to-phase voltage of Vn is equal to 5.5 kV, fed by a network with a maximum short circuit power of S. Short circuit is equivalent to 250 MVA. So this is the solution. We can see here to get the C here, we will use this formula. So rearrange this formula, and then we get C is equal to Q divided by omega Vn square. So by put all the value, we can get the value of C. Okay, omega is equivalent to 2 pi F. Okay, then we have to calculate what is the L up. Okay, L up by using this formula. So this formula for L up. So we choose this formula, which is Vn square divided by S and also divided by omega. So omega must be put in the input in here to get the L up. So we get the value. This one is the omega. and this one is the S. Then we have to calculate what is the iron rush ratio to the IN capacitor. So by using this formula, okay, by putting all the C and L up value, then we get the value is 45. 45 means that the peak of the inrush current is 45 times from the nominal current. So the value is very, very high. So then we have to calculate what is the F naught by using this formula. Okay, then we put all the L up and C value, and then we get the F naught is equivalent to 1582 Hertz. So we can see that the maximum inrush peak current is equivalent to 45 times the bank nominal current in this example, and its natural frequency is 1582 Hertz. Okay, next is a protection of low voltage capacitor bank. Okay, this is the requirement for the capacitor bank. Okay, the allowable capacitor bank's overload is only 30%. This is the standard range, and the variation due to tolerance of capacitor value may lead to a current increase of 5%. Okay, but by using this standard, it allows a tolerance of 50%. So from 5% and 3%, we can get the cumulative effect of both phenomena, means that the equipment must be sized for a current of 1.3, which is 30% overload, times with 1.05, which is 5% current increment, which is equal to 1.37 times the capacitor bank nominal current. So this is the value that we have to consider when we design the capacitor bank. Okay, then low voltage capacitor protection can be provided using a fuse or circuit breaker. So there are two types of protection for low voltage capacitor, which is by using a fuse or circuit breaker. And for circuit breaker protection, okay, the rating must be above 1.37 I nominal capacitor, and thus the thermal threshold must be set at 1.37 I nominal capacitor. Okay, then for fuse protection, to avoid the risk of the fusing after a large number of switching operation, the rating must be greater than 1.6 I nominal capacitor. This is the requirement for the circuit breaker and a fuse protection. Okay, that's all for 6.5 subtopic, which is capacitor band protection. Thank you.